In this lecture here, we want to continue talking about transformation of functions. So in the previous lecture, what I did is I walked you through some of the basic parent functions, specifically the constant function here, the identity, the absolute value, the quadratic, the cubic, the square root, and the cube root. And now what I want to do is I want to take these parent functions here, okay, these seven main ones, and what I want to do is I want to talk about, what happens when I add 2 to it, or I put in parentheses x minus 1, say here, like what does the graph of f of x is equal to, now it's x minus 1 squared instead of x squared, or what does the graph of f of x is equal to 1/2 x cubed look like? How does it compare to the parent graph? And so what we're going to do is we're going to talk about these transformations. So these are the transformations we're going to work through. We're going to talk about first vertical shifts to graph functions right here. Then we'll talk about horizontal shifts. Then we'll talk about reflections to graph. We'll do vertical and horizontal stretching and shrinking. And then the last thing we'll do is we'll do a sequence. So we'll do multiple things. So what I'm going to walk you through first is just what does a vertical shift look like? What does a horizontal shift look like? What is reflection, vertical stretching, horizontal stretching or shrinking? And then what we'll do is we'll do a combination of all these things. You can see one example there. Okay, so the first one is the easiest one. This is vertical shifts. Okay, so we're going to let f be a function and c be a positive number. Okay, positive real number. The graph of y is equal, so you're going to take so f of x here is going to be the parent function. Okay, it's going to be one of these 7 parent functions here. Let me go back. It's going to be one of these 7 parent functions right here. Okay, f of x. And what you're going to do is you're going to take to it and you're going to either add or subtract c to it. Okay, so the graph of y is equal to f of x plus c is the graph of the parent function shifted c units vertically upward. And the graph of y is equal to f of x minus c is the graph of y is equal to f of x shifted c units vertically downward. So basically, here's what's going on. I'm going to just do a generic example here for you. Suppose you have a graph that looks like this, okay? Just some random graph, okay? Just something, this will actually be the square root, and this will be f of x. If you do f of x plus c, what you're doing is you're moving the graph. It's going to be the same graph. It's just moved up c units. Okay, that's all it is. Similarly, if you do f of x minus c, it's the same graph, just moved down c units. That's it. So here's your parent function. When you add the plus c, you're just shifting it up. And when you subtract the c, you're just shifting it down. And that's it. All right, so here's an example. So we're going to use the graph of f of x is equal to the absolute value of x to obtain the graph of some new function, g of x, which is the absolute value of x plus 3. So what you're seeing here is g of x is equal to, well, the absolute value of x is just f of x, and then I'm adding 3 to it. So all you're going to do is you're going to shift vertically. You're going to shift, so in blue here you see f of x. You're going to shift it up 3 units. So if you look at these points here, here's 0, 0. You're going to add 3 to it. So the new turning point here, this is going to be the point 0, 3. Similarly here, this is the point 2, 2. When you add 3 to the y, it becomes 2, 5. Over here, negative 2, but the absolute value of negative 2 is 2 plus 3 is 5. So you're literally just moving every point of the graph up 3 units, and that's it. Similarly, let me just show you just real quickly here. Here's the absolute value of x. Real crude. If you were to do g of x is equal to the absolute value of x minus 5, you would just be moving it down 5 units. And that's all it is. Okay, so when you add c, you move the graph up c units. When you subtract c, you move the graph down 5 units. Very, 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 very simply. Okay, so all I'm doing is I'm transforming my f of x with a vertical shift here, okay, either by adding c units to it or subtracting c units to it. All right, now horizontal shifts are a little different. Okay, and I always say this because it works the opposite way you would think, and that'll make sense when I show you the example here. So let's let f be a function and c be a positive real number. Okay, so like let's look at, choose a different one. Okay, so f of x is equal to x squared. So that graph looks like this. Okay, it's the parabola. The graph of f of x plus c. So now what's going on here? Let me show you this one. Okay, so this will be, let's do f of x plus 2. So that would be x plus 2 squared. Okay, is the graph of f of x is equal to y is equal to f of x shifted to the left c units. So when you have a plus in here, I know it seems weird because you think plus you go to the right. But whenever you have plus 2 here, you're going to move it to the left c units. So here's 0, 0. You're going to take this graph. Notice how it's x plus 2. So this shifts x squared to the left 2 units. So it's going to be the same graph here. So this is my y is equal to f of x plus 2. So this is x plus 2 squared. Similarly, the graph of y is equal to f of x minus c is the graph of y is equal to f of x shifted to the right c units. So for example, if I ask you to find this graph, this minus 3 underneath the parentheses here means to shift x squared to the right. In this case, c units. Well, my number here is 3 units. So you would literally take the graph, and this one here would be f of x minus 3 would be x minus 3 squared. You're just shifting to the right here. So this is what I mean when it works the opposite way you think. If you have a plus underneath the exponent here, it shifts to the left. If it's a subtraction, it shifts to the right. So let's take a look here with the square root function. So use the graph of f of x, okay, to obtain the graph of g of x, which is the square root of x minus 4. So what g of x here is, it's the same thing as f of x, but instead of x, it's x minus 4. So you have the minus underneath the square root. So this minus 4 underneath the square root tells me to shift, now going back, x minus c here, shift to the right 4 units. So in blue here, what you're seeing here is you're seeing the square root of x. So I'm going to take my every point along the graph and shift it 4 units, and that's going to get me my new graph. So in blue here, this is what the graph of the square root of x looks like, and in this little bit of red here, okay, it's the square root of x minus 4. So you could similarly do it this way. Suppose I ask you to sketch g of x looks like the square root of x plus 2. So here's the square root of x. Well, the plus underneath the square root sign, so plus 2 means shift to the left 2 units. So I'd take my graph, shift it to the left 2 units, and this would be the square root of x plus 2. Okay, so it's the same graph, just whoop, shifted to the left 2 units. All right, now let's talk about reflections. So reflections about the x-axis. So if you have the graph of y is equal to negative f of x, is the graph of y is equal to f of x reflected about the x-axis? So let me just, I don't want to do the same one here. So if you take this one, for example, this is the squared. If you were to sketch the graph of y is equal to negative x squared, to reflect it along the x-axis, you'd go, whoop, you'd flip it down. So it would be like this. Okay? So that's when there's the negative in front of it, okay? So when you have a reflection about the y-axis, okay? So if I say the graph of y is equal to f of negative x, is the graph of y is equal to f of x reflected about the y-axis. So for example here, if you were to look at y is equal to x cubed, that looks like this. That's the cubic. If I were to say now sketch the graph of negative x cubed, okay, well notice how the negative is inside or underneath the exponent here. You'd flip it around the y-axis. So you'd take this and reflect it around this way. And this would be y is equal to negative x cubed. Okay. Let's try this one now, okay? So use the graph of f of x is equal to the third root of x to obtain the graph of h of x is equal to the third root of negative x, okay? So notice here what this is. H of x is the same thing as f of negative x. So it's the third root of negative x. So in blue here you can see the third root of x. It looks like this, okay? Pretty terrible sketch on top there, but you got it. That's third root of x. So notice how you have negative x here. Okay, so what that's telling you is to take it and reflect it around the y-axis. So you're going to take this and look, when you reflect it around the y-axis, it literally flips the graph along the y-axis like that. So that's what this graph would look like, transforming it from its parent function. All right, now let's talk about vertical stretching, okay? So let's let f be a function and c be a positive real number. If c is greater than 1, right, the graph of y is equal to c of f of x. So you're taking f of x and multiplying it by c. Is the graph of y is equal to f of x vertically stretched by multiplying each of its y coordinates by c. So what does that mean by vertical stretching? Got a little bit of a sound effect there. Okay, just want to make sure I don't do the same thing here. So this is x squared here. If you were to look at y is equal to 4 times x squared, notice how this number in front of the x squared here is greater than 1. What you would do is you would take each y value and you'd multiply it by 4. So instead of the point, 1, 1, it would be 1, 4. So you'd go whoop, like this. Okay. Now, if your value is between 0 and 1, okay, the graph of y is equal to c of f of x is the graph of y is equal to f of x vertically shrunk, okay, by multiplying each of its y coordinates by c. So it would look like this. So this is y is equal to x squared. If you were to look at something like this, y is equal to 1/2 x squared. Notice how this is between 0 and 1, this value in front. So this graph, you're going to take the values here and you're going to literally pull them down. So instead of being like the 0.24, it'd be 2.2. Instead of the 0.39, okay, it would be 4 halves, excuse me. So it would look like this. So you're getting pulled down. You're shrinking it. You're shrinking it downward. Okay, so then this one is this. So let's try this one. So use the graph of f of x is equal to the absolute value of x to obtain the graph of g of x is equal to 2 times the absolute value of x. Okay? So what's going on here, notice the 2, okay, is greater than 1. So what's going on here is you're stretching the graph. And so you're stretching right here. Stretching because it's greater than 1. So notice, looking back here, notice how when I stretched x squared, it kind of like brought the graph in and pushed it up quicker. So this is what you're seeing. Here's the absolute value of x, like this, and it's going up. It's stretching faster, so it came inside because you're multiplying all the y values here by 2. On the same graph, so if you were to look at some new function, we'll call h of x is equal to 1/2 the absolute value of x. Well, just, like see what would happen here. So it would look like this instead. So it kind of got like pushed down, as we say. Okay. Now let's talk about horizontal stretching and shrinking. Okay. So let's let f be a function and c be a positive real number. Okay. If c is greater than 1, the graph of y is equal to f of c of x is the graph of y is equal to f of x horizontally shrunk. Okay, so that's like pushed down by dividing each of its x coordinates by c. Okay. So this would be something like this. Just make sure I don't do the same one. Oh, it's good. Okay, so let's look at this one right here. So this is the square root of x. Okay, so if you were to look at something like this, square root of 2x, okay? So just kind of like think what's happening here, right? So 0 stays the same, okay? But if you were to do 2, okay, you would get to 4 quicker. So it would kind of be looking like this. It'd be like you're pulling the graph in. You're shrinking it. It would look like this. A little bit of a typo. I'll move that. So this is f of x is equal to square root of 2x. So when c is greater than 1, it's like you're pulling the graph back towards in on itself. Okay. Similarly, or kind of the reverse here, if c is between 0 and 1, then the graph of y is equal to f of c of x is the graph of y is equal to f of x horizontally stretched. So you're pulling it. Okay, so for example, here's the square root of x. If you were to look at f of x or some g of x is equal to 1 square root of 1/2 of x, it's like you're stretching it, you're pulling it out. Okay, like that. So that's what I mean by horizontally shrunk, you're pulling it in. All right, horizontally stretched, you're pulling the graph out. All right, so here's an example here. Use the graph of f of x is equal to x squared, so you're seeing that in blue here. To sketch the graph of g of x, now underneath the squared here, so you see how you have 1/2 x, the quantity squared. So you're going to stretch the graph. So you're going to pull the graph out like this. And that's what's going on here. All right. So you're dividing each of its x coordinates by c. So for example, if you were to take 2 and divide it by 1/2, it'd be 2 times 2 to get you that 4 there. So that's what's going on there. Okay. Let's do a big sequence here. All right, so let's use the graph of f of x is equal to x squared. So in blue here, okay, this is f of x is equal to x squared right here. All right. To obtain the graph of this, okay, so there's a lot going on. G of x is equal to negative 1/2 and times, and then in parentheses, x plus 1 squared minus 2. All right, so it may seem weird here, but you're just going to follow the order of operations here to do this. Okay, so here's x squared. So the first thing I'm going to do, you see how I have this x plus 1 in underneath the parentheses here? All right, that tells me I'm going to move to the left 1 unit. Okay, so I'm going to take my parabola and basically, look, I'm moving it to the left 1 unit. All right, then notice how I have this 1/2 in front. Okay, so what does this mean? This means I'm going to vertically shrink it. So that means I'm going to pull it down. And then what does the negative in front mean? The negative means flip it on the x-axis. So now all of a sudden it looks like this. And then finally, what does the -2 do? Then the -2 says move it down 2 units. So that's what I did. Look, I moved it to the left 1 unit. I vertically shrunk it. Whoop, that's because that 1/2 in. And then I did the negative. I flipped it. And then finally, I did a vertical shift down 2 units. All right. So a lot going on here. But, you'll get a chance to practice this in the homework. And, if you, again, as always, if you have any questions, just let me know.